What I learned in my walkthrough is I probably need to talk fast. So we'll see how it goes. Okay, so quick summary, a couple of slides for a quick summary of Alaska. Big earthquakes, big volcanoes, big glaciers, fast rates of processes. So this is a high signal to noise environment. I'll show you more on the earthquakes and these other processes as well. Another key point is spatial variations. So there's spatial variations in input, things like subduction obliquity, amount of sediment in the trench, hydration of the downgoing plate, and also in the outcomes, the way that the process or the system behaves. So interseismic slip deficit varies tremendously along strike. Seismicity in the slab varies along strike. Creep behavior, volume flux, and chemistry of magnetism. All of those things vary significantly along strike, and in some cases, relatively abruptly. Okay, so some of the key advantages, and this is put at the beginning because I might not get to the very end of the talk, we'll see. The key advantages for faulting and earthquake cycles is large and great earthquakes within the instrumental record and are likely in the future. So the rate of large earthquakes is a little bit slower than Chile, but not a lot slower than Chile. And importantly, we have quantitative information about patterns of coseismic, postseismic, and interseismic creep and slip on the interface, and also of slow slip events. So we know, for example, in places where there was post-seismic afterslip following 1964 earthquake and has also had long-term slow slip events. So because we actually know where different kinds of slip happened over time, we know if different modes of slip happened in the same place at different times. Magmatic drivers of eruption. There are eruptions at a wide variety of scales and highly varied volcanic behavior. And in terms of landscapes and seascapes, although sparsely studied in most cases, there are many landslides, very rapid erosion and exhumation, and very large amounts of sediment that get mobilized. So quickly, in terms of earthquakes and tectonics, on the east end here, this is a strike slip system on the very east, which transitions to the subduction zone. And right in this corner there, and I'm sorry that you can't really see, but I guess I don't have a functional mouse either. Anyway, at the corner where it goes from strike slip to subduction, there's actually a section in the St. Elias Mountains that is much more like continental collision. So the subduction zone has been basically plugged up by overthinking topography. Whereas the rest of the subduction zone is more classic underthrusting. The plate rates are about 5 centimeters per year in the east, about 6 centimeters along the Alaska Peninsula here, and then about 7.5 to 8 in the Western Aleutians. And also the obliquity changes dramatically. So it's straight on subduction at the Shumagon Islands here on the Alaska Peninsula, kind of in the middle of the plot. And the obliquity goes one way to the east, and in the west, westernmost Aleutians, it's so oblique, it's almost a strike slip boundary by the time you reach the Russian part of the Western Aleutians. The pink blobs are the rupture areas of the last set of great earthquakes. And so almost all of the arc has ruptured with a few little gaps. However, if we look at the interseismic data, the purple patches are areas which we infer to be locked or dominantly not moving in between. The yellow patches are those that are creeping, or at least dominantly creeping. And so again, we have these key boundaries. So even within the 1964 rupture, there was a gap of relatively low slip that is today characterized by dominant creep. And then along the Alaska Peninsula, there's a region there which is dominated by creep. In fact, along the very end of the Alaska Peninsula, we have abundant GPS data. We see zero strain. It could be Kansas for the amount of strain that we are seeing, and it's right over in the forearc of a subduction zone. And the same sort of pattern continues further to the west. So in addition to having those variations, what we found is along the Alaska Peninsula in particular, that the model or the interseismic data are better fit by abrupt transitions. Now, that doesn't mean that they're necessarily instantaneous, but a model in which there are sort of segments with characteristic slip deficit actually fits better than one where you smooth across those boundaries. And so the two figures have the same white contours, which are the slip contours of the Simeonoff earthquake from July 2020, but different backgrounds. The two different backgrounds are two different interseismic models that use the same data, but different assumptions about how you regularize the problem. So I don't have a time to go into all of the details, but basically the same segment boundaries are present, but they look rather different because there's a lack of resolution offshore. So the model on the left assumes that the slip deficit is maximum at the trench and decreases down dip, whereas the one on the right assumes that there's sort of a Gaussian shape to the slip deficit distribution. Slip deficit, since I haven't defined that, I should define that. It's the difference between the long-term plate motion rate and the slip that's actually happening. So if the interface is not moving at all, there's a slip deficit equal to the plate motion rate. So we find that the coseismic slip did appear to change at the interseismic segment boundaries. So the Simeonoff earthquake didn't go past this boundary right there that's intermittently showing up with the little red pointer. And then to the Chignik earthquake ruptured the segment to the east. We've also tried to look at slip budget as a function of not just along strike, but also along dip. And so this is the same figures that you see here on the bottom, though. The red curve is the slip as a function of depth in each of the two rupture segments. So the red curve is the slip in the earthquake. The blue and the green are the two different interseismic models. They look a lot less different when you plot them this way than they do when you colorize them up on the top. But the key point in either case is, regardless of which interseismic model you're looking at, the earthquake used up a century's worth of slip deficit from the depths of about 25 or greater than about 25 kilometers. However, it did not use up all of the slip deficit that was accumulated over the previous century at the shallow part. So the question is that going to rupture? There's room for another similar sized earthquake at shallow depth. Is that going to happen later? Is that slip going to happen as post-seismic creep? Or are those interseismic models actually wrong? And if we had better data offshore, we would actually see that there wasn't so much slip deficit as we thought. All of those seem to be possibilities. If we now put in purple, there is the 21 Chignik earthquake, magnitude 8.2. It ruptured a similar depth range as the Simeonoff earthquake. And the interseismic slip deficit is now shown in grayscale on this figure. And in the blue colors are two different versions of the estimate of the slip region for the 1938 earthquake, which was the last one in along that segment. And we think that 1938 probably ruptured the shallower part of the interface based on tsunami modeling. However, it couldn't have had a lot of slip. The average slip in 1938 was only a few to several meters. So it was a relatively low slip event, kind of comparable in terms of slip maximum, probably even perhaps similar to or smaller than the Chignik event. So we have room to figure out actually what's happening in those shallow parts of the subduction zone, which are the most tsunamigenic, and trying to repeat this kind of analysis for other areas. Now, I mentioned slow slip events. Cascadia is really famous for these. Alaska has some events that are like Cascadia, but it also has these very long-lived events. So you can see with the circles, the oval areas that are dashed, these are the outlines of long multi-year slow slip events. These have durations of 2 to, in one case, at least 9 years. We don't actually know an upper limit because it had already started by the time we were making GPS measurements in the area. So these are equivalent to magnitudes as large as upper 7, about 7.8 in one case. We also see some smaller short-lived events that last a few weeks. But there are some segments in Alaska where we have data but appear to not have slow slip events, or have only had maybe 1 or 2 in a 20-year time period. So not everywhere has the same events. There are some variations in behavior. Okay, how much time do I have left? Well, I'm going to move on to volcanism. 10 minutes. Oh, okay, I might actually get through all this. That's good. Okay, in terms of eruptive volcanism, Alaska has 52 Holocene active volcanoes, actually 53 now, since one that hadn't been active for a while became active. Alaska has roughly 2 eruptions per year, plus every year there's a few volcanoes showing unrest that don't erupt. It has systems, open system type volcanoes like Pavlov and Cleveland with very frequent eruptions. Those actually produce, in fact, very little deformation that we can see. It has a number of large calderas, and in fact, in the Holocene, there are several very, very large caldera forming eruptions. Some of these volcanoes were very big. So like Mount Veniaminoff on the Alaska Peninsula, at its base, it's on the order of 25 kilometers diameter or so, and about 2,500 meters elevation. So Okmok was probably a similar sized volcano before it blew itself up a couple of times in the Holocene. There's also variation in volcano seismicity and bulk chemistry. So this figure comes from Berman et al. 2014. In the top figure on the colors, the red, yellow colors are basically density of earthquakes. And you can see that depth goes to 50 kilometers on the bottom. So this includes lithospheric depth events beneath the volcanoes. You can see that there's some systematic variation. So for example, some areas there are lots of relatively deep earthquakes. In other areas, there are none or very few. The green diamonds are actually based on the data on the bottom. That is the median SiO2, so basically how silicic the volcanism is. And you can see that that also varies systematically along the arc, and there is some relationship to this. So for example, in this segment that sort of over there, anyway, most of the way over to the right, but not all the way, you see where you don't see an abundance of deeper earthquakes, you also see higher silica, higher silica volcanism. So volcanic earthquake depths and silica show similar along arc trends. There are other elements of chemistry that also show systematic along arc trends. And Berman et al. Concluded that regional subduction processes control volcanic activity. So this could be a variation in the magma productivity at depth, or it could also be a variation in how much magma makes it up through the crust, which depends on the state of stress. This is a quick summary from the Alaska Volcano Observatory of eruptions 2005 to 2021. If I made a longer window on the plot, it would go off the page. In terms of number of eruptions, Cleveland volcano in the Central Aleutians is the top. The biggest one at Cleveland was actually just before this. It was in the early 2000s. It was bigger than any of the ones that are shown here, but it is the top one. It has just been instrumented actually more intensively. So I think you'll hear about that shortly. Veniaminoff, whoops, didn't mean to go back. Pavlov is also, again, relatively open. Veniaminoff is very different, but also very, very active in terms of number of eruptions and so on. I'm going to show you a little bit about one of these, Okmok in 2008. It's a little bit of favorite spot syndrome, but it does actually have some useful things to say. So this is a little bit about deformation. I'll briefly talk about that, but also about the effects of the eruption in terms of land surface. So this is Okmok. It's in the eastern Aleutians. The caldera is about 10 kilometers across, and the most recent caldera forming eruption was about 2,000 years ago. So what you see here, pretty much everything you see except the water in this photo is Okmok 2008 eruptive deposits. It was very explosive as a result of interaction of magma and groundwater. And so the piles or the thickness there is at least, well, it's tens of meters basically of tephra. This is all basically airfall. Everything you see the canyon here, this canyon formed in no more than 2 melt seasons. That is, this photo was taken in 2010. There had been 2 snow melt seasons, and the erosion is most rapid during the snow melt season. The whole canyon was carved in that time because the materials were not present more than 2 years before the photo was taken. There's actually a campaign GPS marker that's somewhere down there. That's actually why I was in this area with a helicopter, but it was about 35 meters down, unfortunately. So what's below Okmok, this is an interpreted structure from Wang et al. 2021. Okmok has a magma body at very shallow depth. Estimates have ranged from about 2,000 to 3,000 meters below land surface. And it's located right, basically, the magma body seems to be located right under the center of the caldera. So the 2008 eruption formed this new cone called Ahmanalik, which is a new pathway for magma, the one on the left. The pathway on the right goes to a cone that had been the source of all the 20th century eruptions prior to the 2008 eruption. And just to show you a little bit of what we can learn from geodesy, on the left is actually the time history of deflation, basically depressurization of the magma system during the 2008 eruption. On the right is the reinflation of the magma system after the eruption. And on the right, I'll sort of concentrate on this figure on the right. This is a total volume change inferred from a simple pressurization model. But what you see is a series of basically exponentially decaying inflation pulses that occurred at Okmok. And one thing that's rather interesting is the time scale of the decay is actually decreasing with time. So that has potential implications for how the magmatic plumbing system must be evolving, because if there was no change in the system, you'd expect actually the same time scale for decay. So something has to be changing in the system to get a changing time scale. So to finish up with landscape processes, this is a photo I took this summer of the Copper River Delta. It's really just kind of a pretty picture, but this suspended sediment plume is pretty epic. So suspended sediment load has been measured as high as 1,800 milligrams per liter. So that's an enormous number. When I looked at things like Mississippi River and flood, you get often numbers that are 10% of that. So it's an enormous amount of sediment. The sediment flows into the trench and down the trench all the way out to the central Aleutian. So it's not just Copper River, but also from Cook Inlet, but sediments from the continent coming from here and a couple other systems really fill the trench to a remarkable degree all the way out to the central Aleutians. This is a figure from Higman et al. 2022. Hig is going to be showing an updated or expanded version of this at the AGU. He put 100 giant Alaska landslides. I'm not sure exactly how big they had to be giant, but anyway, he's showing a larger segment. I'm going to focus in on one of them, which is right there. This is Barry Arm. So this is one that I actually had a role in helping to discover. This is the landslide itself. So this is within Prince William Sound in a fjord that is in the process of deglaciating. So we discovered this landslide as part of a project to look at topographic change by looking at digital elevation models. And when we first looked there, we thought there was an error in the data because there were tens of meters of elevation change that had occurred. And anyway, we realized after a little while, it turns out that Peter Heusler and I had been in the fjord and had photos, and you could see the landslide scar. We looked at things again, and indeed there is the landslide. So, so the upper left is the surface elevation change in meters. It's minus 40 to 40 meters. So there's tens of meters of elevation change of this landslide. And we also know when this landslide started to move in a serious way. Berry Glacier has been retreating. So you can see in the colors the extent of the glacier, and basically the glacier retreated past the current location of the landslide in about 2006 to 2008. And immediately after the glacier retreated, the landslide started to accelerate. So the landslide was clearly being buttressed in some respect by the glacier. And this particular landslide is now being monitored because of the potential for hazard. Okay, this is actually the last slide, so I will make it through here. So a little bit on volcanic sediment. This is a couple of photos taken near the town of Perryville on the Alaska Peninsula. On the one on the left, you can see there's some areas, sort of linear zones where the vegetation is darker. Those are actually beach ridges. So there's a whole series of beach ridges that are not just in this one spot, but along through this whole section. And in my non-expert eye, looking at the landscape in this area, it really looks like a landscape that's simply been drowned in volcanic sediment. It's sediment that comes off of Veniaminoff volcano. These are not mud flows. These are simply sediment, plastic sediment derived from the loose volcanic materials that really fill up what were previously eroded valleys. So again, it's an example of very, very large amounts of sediment that are mobilized associated with volcanic processes and affecting the landscape. So any time for questions? Probably not, but we'll see.
Thank you, Jeff.